You are settled into a quiet seat aboard a small spacecraft, floating far from home in a calm and endless dark. Outside the window, the stars look steady and gentle, like tiny, patient lamps hanging in a black corridor. The cabin around you is dim, washed in a soft, muted glow from a few small panels. There is just enough light to feel safe and oriented, but not enough to keep you awake. You feel the faintest vibration through the seat, more a slow, steady purr than a motion. It's a reminder that this little ship is coasting smoothly through space. If you like, you can imagine a blanket over you, the fabric warm just enough for your body to feel heavy and supported, with nothing you need to do and nowhere you need to be. Tonight, this small spacecraft is your front row seat for a very slow journey, one that traces sunlight and shadow across every planet in the solar system. Out here, far from city lights and busy days, you can simply watch in your mind as each world turns and tilts. Each planet drifts through the sun's glow, casting long, quiet shadows into the dark. You do not have to remember names, numbers, or details, they can move through you like passing clouds. The parts you find soothing can stay, while everything else can fade. As you rest here, your mind follows one simple, quiet question: how does sunlight touch each world, and what do those shifting patterns of light and shadow reveal about the planets we call our neighbors? Your spacecraft glides in silence beneath this question. You can picture the sun behind you, a bright, steady star pouring out light in all directions. It sends a vast invisible rain of energy across space. Each tiny beam races outward at the speed of light, crossing the gap from the sun to Earth in just over 8 minutes. That distance, about 93 million miles, 150 million kilometers, is nothing to a photon. Most beams miss everything and keep traveling forever, but a small fraction strike planets, moons, rings, and even the thin dust floating between worlds, revealing their presence. When sunlight hits solid ground, it can be absorbed and turned into warmth, or bounced back into space, or scattered in all directions, depending on the surface. On bright clouds, light scatters and glows, creating a soft sky. On dark rock, more light is swallowed. That leaves sharp shadows and deep contrast. Where light cannot reach, a shadow forms, not because anything is added, but because the rain of sunlight has been blocked. What remains is a calm, unlit patch of ground or space behind whatever stands in the way. On every planet, the dance of light and shadow begins with one simple fact: the planet spins. As it rotates, different parts of its surface take turns facing the sun and then turning away, creating a rhythm of day and night, with dawn and dusk marking each shift. A day on any planet is just the time it takes to complete one full turn. That spin decides how quickly sunlight moves across its landscapes. On Earth, the spin takes about 24 hours, a pattern so familiar that your body has grown its own internal clocks. Those clocks expect morning light and nighttime darkness without conscious thought. When the sun is high, shadows shrink beneath objects. When it sits low near the horizon, shadows stretch long and quiet, reaching across the ground like dark fingers. Now imagine the same pattern on every planet: on baking Mercury, on cloud-wrapped Venus, on the gas giants and the icy outer worlds. Each world carries its own rhythm of illumination, its own choreography of turning landscapes beneath a distant star. Your spacecraft drifts along a path that will eventually carry you past each of these worlds, one after another. There is no hurry. Space gives you all the time you need. For a moment, let your attention settle on your breathing, smooth and easy as a planetary turn. Long before spacecraft and telescopes, humans watched Earth's cycle of light and darkness and wondered what it meant. Every sunrise, sunset, and shifting season hinted that the sky was not fixed, that the sun's path changed, and that shadows behaved differently over time. People saw the sun rise from slightly different points on the horizon as months passed. They noticed midday shadows growing longer or shorter with the seasons. In summer, the sun climbed higher; in winter, it stayed low, stretching shadows and cooling the air. From these quiet observations, long before city lights or alarm clocks, humans sensed that Earth must be moving and tilting, changing how sunlight fell across its surface. Imagine someone centuries ago using a simple stick to watch a shadow move like a silent clock hand. At midday, the shadow was shortest. At sunrise and sunset, it stretched far. Over the seasons, its length at midday changed gently, tracing the invisible geometry of Earth's tilt. We humans eventually realized that Earth's axis is tilted, not straight up and down. This tilt controls how sunlight is shared between hemispheres during the year. When your part of Earth leans toward the sun, light arrives more directly and stays longer, creating summer. When it leans away, the light weakens and shortens, and winter settles in. All of this, seasons, climate zones, the length of days, comes from the way Earth spins and tilts in sunlight, creating shifting patterns of brightness and shadow. Now, as you rest in your quiet spacecraft, you can imagine looking back at Earth from above. You see the bright side turned toward the sun and the dark side facing night. A thin glowing line circles the edge, the twilight zone where the sun sits just below the horizon, painting a gentle gradient from day into night. That line is always present. It slides endlessly across the planet as Earth turns, a moving frontier between light and dark. In your mind, you can watch city lights flicker on in the dark half, pinpricks of artificial starlight rising wherever sunlight has faded and darkness returns. Closer to the poles, the pattern shifts. In some seasons, twilight lingers, stretching dawn and prolonging sunset, or creating months where the sun never fully rises or never fully sets. These regions reveal how sensitive light and shadow are to tilt and geometry. They remind us that even on one planet there are many ways to experience a day. Now gently shift your imagination outward, away from Earth, toward other planets sharing the sun's light along distant orbits. Each world turns in its own rhythm. Some spin quickly, rushing through short days with fast-moving shadows. Others turn slowly, stretching a single sunrise into something that lasts for weeks. Some worlds have thick atmospheres that scatter sunlight, others have almost no air and cast razor-sharp shadows. Distance from the sun also matters. Light weakens as it spreads, like a campfire fading as you walk into the dark. Near the sun, light is fierce. Farther away, it becomes pale and gentle, so that even noon on the outer worlds can feel like a bright kind of dusk. For now, your spacecraft cruises between the orbits of Earth and Mars, the sun still bright behind you, the inner planets arranged ahead on their invisible tracks. You might picture faint lines marking those paths, delicate rings drawn around the sun somewhere below. Mercury hugs close to the sun, turning slowly under brutal swings of day and night. Venus spins beneath a blanket of cloud, its surface hidden from ordinary light. Earth and Mars move farther out, with rocky ground where shadows fall across hills and dust. Beyond them wait Jupiter and Saturn, vast spheres of storm-striped clouds, and even farther lie Uranus and Neptune, cold and distant, lit by a sun that appears little more than a bright star. Your journey will drift from one world to the next in time. But this first part of the voyage is about understanding the stage on which all patterns of light and shadow unfold. The stage is the solar system itself, a star at the center, planets in orbit, each one spinning, tilting, and moving through the sun's steady light. Every shadow on every planet, no matter how strange, comes from the same geometry, beams of sunlight flying straight and worlds turning slowly beneath them. You do not need equations or perfect angles, it is enough to sense each world posing before the same lamp. Back in the cabin, the hum of the spacecraft feels steady and reassuring, like a quiet fan in a darkened room. You can let your shoulders loosen, your jaw rest, your hands unclench. Your thoughts can stay soft, following these images only as far as feels comfortable. Outside, the sun is not visible through the side window, but you can sense it somewhere off to the side, the source of every beam that will illuminate the planets ahead. As your small ship continues its smooth, silent path, you are ready to drift inward at your own pace. You will soon begin watching how sunlight and shadow behave on other worlds, one slow step at a time. Your small spacecraft still drifts in the dark, steady and calm, exactly where you left it at the end of the last chapter of your journey. You are still in that comfortable seat, wrapped in quiet, with the dim cabin lights resting softly on the panels around you. Nothing has rushed forward without you. The solar system is patient, waiting for your attention to wander wherever it feels most relaxed. Outside the window, stars remain fixed and gentle, but now you can imagine the invisible paths of the planets more clearly, like faint chalk rings drawn around a distant lamp. Each path marks a year for a different world, a slow, repeating loop of sunlight and shadow. Your ship floats above these unseen tracks like a watchful observer on a balcony, looking down at a cosmic roundabout. You are here mostly to listen and picture, not to steer. Before you look closely at any planet, it helps to think for a moment about the sun itself. You can imagine it somewhere behind you, a sphere of incandescent gas about 864,000 miles across. Its surface seethes at thousands of degrees, bright enough that even at great distances, a tiny fraction of its light can warm solid rock and thin air. To every planet, it is both a lamp and a clock. The sun shines because deep in its core, hydrogen atoms are pressed and heated until they fuse into helium, releasing energy as light and heat. This energy takes a long, winding path outward, bouncing around inside the sun before it finally escapes into space as sunlight. By the time those photons reach the planets, they are spread thin, but still organized in straight beams. When they strike a world, they carve out patterns of illumination and darkness. The farther a planet is from the sun, the more those beams have spread out, and the dimmer the sunlight becomes. Physicists describe this with the inverse square law: double the distance, and the light becomes 4 times weaker. You do not need the equation, it is enough to picture a flashlight shining on a wall, getting dimmer as you step back. The outer planets live where the beam is very wide and soft. Closer to the sun, the story is very different. Near the center of the solar system, sunlight can be brutally strong, unfiltered, and unsoftened. Shadows there are sharp and high contrast, because there is so much more direct light to block. Planets that hug the sun feel extremes of baking day and freezing night, with little atmosphere to smooth things out. Your first planetary stop will be one of those worlds, Mercury. You can imagine your spacecraft gently adjusting its path, almost imperceptibly, so that it will pass near the innermost planet. There is no lurch, no sudden sensation, it is more like a slight change in the direction of a dream. Through the window in your mind, the sun grows larger, its glare intense enough that you might picture protective filters sliding over the glass. Ahead, a small, cratered world waits in the brightness. Mercury is the closest planet to the Sun, orbiting at an average distance of about 36 million miles. Because it is so near, sunlight there is more than 6 times stronger than on Earth. If you could stand on the sunlit side, the sun would look more than twice as wide in the sky as it does from home, a blazing disk pouring down fierce radiation. The contrast between light and dark is extreme. The surface of Mercury is rocky and heavily cratered, similar in appearance to our moon, with no thick atmosphere to soften the view. That lack of air means the sky is black even at noon, and shadows are incredibly sharp, like cutouts with crisp, defined edges. Sunlight strikes the ground almost directly, heating it to about 800 degrees Fahrenheit during the long daytime. In such glare, every boulder casts a dark, precise outline. One of the strangest things about Mercury is its slow spin. The planet takes about 59 Earth days to complete one rotation, but only 88 Earth days to orbit the Sun. Because of the way those motions line up, a full day from one noon to the next on Mercury lasts about 176 Earth days. That means sunlight crawls slowly across the landscape, and a sunrise can feel like a drawn-out event, more like a season than a moment. When the sun finally sets on Mercury, the heat begins to escape back into space, and without air to trap warmth, the surface cools dramatically. Nighttime temperatures can drop to around -290 degrees Fahrenheit (-180 degrees Celsius), a plunge from intense heat to deep cold. The shadows of night are not just darker but also far colder, a reminder that sunlight there is almost the only source of warmth. Day and night are like separate worlds. You can picture your spacecraft hovering above the terminator on Mercury, the boundary between day and night, where sunlight touches one side of a crater while the other lies in darkness. The sun sits low on the horizon, stretching shadows across the ground like long black rivers. As the planet rotates, that line of twilight slowly crawls, revealing new craters and burying others in night. It is a slow-motion sweep of illumination. Scientists learned about Mercury's strange rotation and extreme temperature swings using both telescopes and spacecraft. Radar observations from Earth revealed how quickly the planet spins, by bouncing radio waves off its surface and measuring the tiny shifts in the returning signal. Later, missions like Mariner 10 and Messenger flew past Mercury, and Messenger orbited it, mapping its surface in detail and measuring its temperature. Those missions showed that in some craters near Mercury's poles, sunlight never reaches the deepest floors. Because Mercury's axis is tilted by only a small amount, the sun stays low in the sky at the poles. The rims of certain craters act like permanent walls, keeping their interiors in constant shadow. Temperatures there remain far colder, and radar reflections suggest deposits of water ice hiding in the darkness, preserved by the shade. It is a quiet, surprising image, a world blasted by intense sunlight, yet hiding pockets of ice in permanently shadowed holes. On Mercury, shadow can act like a vault, protecting fragile molecules from the sun's harsh glare for millions or even billions of years. Light and dark are not just visual contrasts, they divide regions into hot and cold, destructive and preserving. The geometry of sunlight decides what can endure. From your vantage point in the spacecraft, you do not need to feel those extremes. You simply watch as Mercury turns slowly, half in day, half in night, caught in a delicate balance between searing exposure and deep freeze. You might imagine the surface glowing faintly in infrared, heat leaking into space from the bright side. On the far side, the ground sinks into stillness, lit only by stars and perhaps the dim reflected glow of the sun from nearby terrain. When you are ready, your attention can drift outward to the next planet, Venus, which orbits farther from the Sun but still closer than Earth. You can imagine your ship easing away from Mercury, the small crater disk shrinking gradually behind you. Ahead, Venus waits like a pale lantern, roughly the same size as Earth but wrapped in thick cloud. It looks smooth and soft from a distance, almost gentle. As your spacecraft approaches, you see that Venus is not a crisp, cratered ball like Mercury. Instead, it is smothered in a bright, reflective veil of clouds that hide its surface completely from ordinary visible light. Sunlight hitting those clouds is scattered and reflected back into space, making Venus one of the brightest objects in Earth's sky. In telescopes, it shows phases like the Moon, crescents of bright cloud against blackness. The atmosphere of Venus is incredibly thick, made mostly of carbon dioxide, with clouds of sulfuric acid droplets. At the surface, the pressure is about 90 times that on Earth at sea level, similar to being deep underwater. Temperatures reach around 870 degrees Fahrenheit, 465 degrees Celsius, hot enough to melt lead, so even though Venus is farther from the Sun than Mercury, its dense atmosphere traps heat very efficiently. Sunlight and shadow behave differently in this heavy air. Because the atmosphere scatters light, the transition from day to night on Venus is not as sharp as on an airless world. Sunlight filters through layers of cloud, creating an extended twilight that reaches into regions where the sun is just below the horizon. Shadows near the surface would be softer and less distinct than on Mercury or the Moon, because light arrives not only directly from the sun but also from the glowing sky. The rotation of Venus adds another twist. The planet spins very slowly and in the opposite direction to most other planets, taking about 243 Earth days to complete one rotation. However, because of its orbit around the Sun, the time from one noon to the next on Venus is about 117 Earth days. Days and nights are long, and clouds swirl high above in complicated wind patterns. Sunlight creeps slowly across the surface, filtered through a permanent overcast. Spacecraft have helped us understand how light moves through this thick atmosphere. NASA's Pioneer Venus missions, and later the European Space Agency's Venus Express and Japan's Akatsuki, observed the planet in many wavelengths of light. By studying how sunlight is absorbed, scattered, and re-emitted, scientists can infer the structure of the clouds and the dynamics of the winds. Even when the surface stays hidden, the behavior of light reveals the layers above it. One of the most striking features seen from orbit is the bright limb of Venus, the edge of the planet where sunlight passes through a long path in the atmosphere before reaching space. That rim glows in ultraviolet and other wavelengths, outlining the planet against the black background. It is like a permanent ring of sunrise and sunset, circling the planet at all times. Your ship can drift along this glowing border, watching the thin band of light wrap around the cloud globe. If you imagine looking downward from orbit, you would not see crisp shadows from mountains or craters on the surface, because the thick atmosphere blurs them. Instead, you would see swirling cloud patterns, bands, and vortices illuminated from above and within. Shadows exist more clearly inside the cloud layers, where one deck of cloud can block light from another, creating complex, layered shade. Sunlight and shadow become three-dimensional inside the air itself. On both Mercury and Venus, the same sun shines, but the experience of light and dark is completely different. Mercury offers a hard-edged, high-contrast world of raw illumination and deep black shadows. Venus offers a hazy, diffuse world where light is softened and trapped within an ocean of gas and cloud. These two planets show you how much the presence or absence of an atmosphere can reshape something as simple as a sunrise. As your spacecraft glides past Venus, you might let your thoughts drift to the early scientists who first studied its changing phases through telescopes. When Galileo saw those phases in the early 17th century, they helped confirm that Venus orbits the Sun, not Earth, because only that geometry could produce the observed pattern of crescents and gibbous shapes. The way sunlight fell on Venus became a clue to the true layout of the solar system. Later, astronomers timed rare events called transits of Venus, when the planet passes directly between Earth and the Sun, appearing as a small dark dot crossing the bright solar disk. By carefully observing these shadows against the Sun from different locations on Earth, scientists could estimate the distance from Earth to the Sun with greater accuracy. A tiny moving shadow became a measuring stick for the entire solar system. Thinking of those transits, you might picture the Sun as a bright circle in your mind, with a small dark bead sliding slowly across it, a planet temporarily interrupting the light. Even at this scale, the idea is the same as a simple shadow. Something solid passes in front of a light source, and an area behind it receives less light. From tiny transits to large eclipses, these patterns help us weigh and map the cosmos. Back inside your quiet cabin, you remain warm and relaxed, far from any real glare or heat. Mercury and Venus have offered you their contrasting portraits of sunlight and shadow, one bare and exposed, the other veiled and softened. You have seen permanent ice in Mercurian darkness and permanent cloud in Venusian brightness, both governed by geometry and physics rather than mystery. You can let these images settle gently in your mind. If you feel your thoughts drifting or blurring, that is perfectly welcome. You do not need to keep track of all the numbers or names, they can fade into the background like distant stars. What matters most is the feeling of slow motion, the awareness that every planet turns under the same sun, each in its own way. Your spacecraft continues to cruise smoothly, humming softly, carrying you outward. Ahead lies Earth, your home world, where daylight and darkness are familiar companions, and beyond it, Mars and the giant planets await. Each will have its own character of light and shadow, its own style of sunrise and twilight, depending on spin, tilt, distance, and air. For now, though, you can stay with the memory of Mercury's sharp silhouettes and Venus's glowing clouds. The journey is long, and there is no need to hurry. Your small spacecraft still drifts in the quiet dark, just where you left it at the end of the last chapter. You are still in that comfortable seat, the soft glow of the cabin wrapping the panels in a gentle haze. Nothing demands your effort. The solar system waits around you like a slow mobile, every planet turning under the same distant sun. Outside the window, the stars look unchanged, but you know that you have slid outward from the realms of Mercury and Venus. Behind you, the innermost worlds continue their harsh cycles of fierce daylight and deep night. Ahead of you lies something more familiar, a planet whose pattern of light and shadow you already know in your body, Earth. You can imagine the ship easing into a path that crosses close above your home world. There is no sensation of speed, only the sense that the blue and white globe is quietly swelling in the window. As it grows, you begin to pick out the curved edge between day and night, the moving frontier of sunlight that sweeps steadily across the surface. From this vantage point, the sun is behind your shoulder, lighting one half of Earth and leaving the other in darkness. The bright side glows with clouds and oceans, while the dark side is dotted with tiny necklaces of city lights. Between them lies the twilight zone, a soft gradient where the sun is just below the horizon, and day gives way to night. On Earth, a day is defined by how long it takes the planet to spin once around its axis. Your body has grown up inside that rhythm, so familiar that you rarely think about it. Roughly once every 24 hours, any one point on the surface moves from sunrise to noon to sunset and into night, tracing a full circle under the sun's steady beam. Because Earth spins from west to east, sunlight appears to rise in the east and set in the west. You can picture the ground beneath you rotating like a slow turntable under a fixed lamp. Where the ground turns toward the light, dawn unfolds. Where it turns away, dusk stretches across the land. Every place spends part of its time in light and part in shadow. The tilt of Earth's axis adds further complexity to this pattern. Instead of standing straight up and down in its orbit, the planet leans by a little more than 23 degrees. That lean means that over the course of a year, one hemisphere tips toward the sun while the other tips away, trading places as the planet completes its path around the star. When your hemisphere tilts toward the sun, sunlight strikes the ground more directly and for more hours each day. Shadows at noon grow shorter, and warmth builds, creating summer. When your hemisphere tilts away, the sun stays lower in the sky, its light spread over a larger area and for fewer hours. Noontime shadows lengthen, and winter settles in. This shifting angle controls how long the day feels and how intense the sunlight becomes. Near the equator, the sun climbs high in the sky all year, and day length changes only gently. Near the poles, the story is more extreme. There, you can have long seasons of very short days and lengthy nights, or periods when the sun barely sets or barely rises. From your spacecraft, you can picture the polar regions as bright caps and dim rings. In some seasons, one pole is tilted toward the sun, bathing it in nearly continuous daylight, while the opposite pole sits in a long shadow. The line between light and dark circles the planet at a slant, showing you, at a glance, how tilt sculpts the pattern of illumination. On the day side of Earth, sunlight filters through the atmosphere before reaching the ground. Air molecules scatter the shorter, bluer wavelengths of light more strongly, painting the sky a gentle blue and softening the contrast of shadows. Under a clear noon sun, shadows are crisp but not as sharp as those on an airless world, because some light comes from the bright sky itself. As the sun sinks lower toward the horizon, its rays pass through a longer path in the air. More blue light is scattered away, leaving warmer hues behind, and the sky can take on shades of gold, orange, and red. Shadows stretch across the ground, growing longer and softer. Sunrise and sunset paint light and shadow with slowly changing color as well as length. At night, in the absence of direct sunlight, the atmosphere still glows faintly with scattered light from distant cities, starlight, and a very faint natural air glow. Clouds can reflect city lights, creating a dim ceiling of color red or orange over populated areas. In remote places, the sky becomes a deep, rich black, broken only by stars and, at times, the pale arc of the Milky Way. The way Earth warms and cools under this cycle of lighting shapes weather and climate. Sunlight absorbed by oceans and land drives winds and currents, while shadowed regions cool and release their stored heat. The daily rhythm of heating and cooling creates breezes, storms, and patterns of cloud, all of which alter how sunlight is reflected and scattered back into space. Scientists study these patterns with satellites that constantly watch Earth from orbit. Instruments on spacecraft such as Terra and Aqua measure how much sunlight is reflected by clouds, ice, forests, and oceans, and how much is absorbed. By tracking these flows of light and heat, we have built a picture of how the planet's energy balance keeps its climate relatively stable over long times. From your quiet seat, you can imagine these satellites as companions in the same night, circling below your ship along tight paths. Each one sees moving belts of cloud and shadow, storm systems casting broad, diffuse shade, and snowfields flashing bright where the sun strikes them. Together, they sketch a living map of how light and dark dance on Earth. Floating near Earth also gives you a clear view of the body that most strongly influences its nighttime light, the moon. You can picture the moon a little distance away, a gray globe half lit by the sun, just as any other world is. The phases you see from Earth are simply the changing angle between sun, moon, and observer, a geometry of illumination. When the moon appears full from Earth, you are on the night side of the planet, facing the sunlit half of the moon. The sun, Earth, and moon lie roughly in a line, with Earth in the middle. When the moon appears as a thin crescent, you are seeing only a sliver of its day side, the rest turned into shadow. Yet at any moment, half of the lunar surface is lit by the sun. The moon's surface, like Mercury's, lacks a thick atmosphere, so sunlight falls directly on bare rock and dust. This creates very sharp, dark shadows, especially near the dividing line between lunar day and night. Astronaut photographs from the Apollo missions show boulders casting crisp, inky silhouettes, and crater rims slicing stark arcs of darkness across sunlit slopes. Because the moon rotates once on its axis in the same time that it orbits Earth, the same hemisphere always faces your planet. A point on the moon experiences a day lasting about 1 lunar month from sunrise to sunrise. That slow turning means that sunlight creeps across the landscape, and the same crater can spend many Earth days in bright light, then many in deep night. When the moon passes directly between Earth and the sun, its shadow falls on the planet, producing a solar eclipse. From space, satellite images show the lunar shadow as a dark spot racing across the Earth's surface, a moving pool of night in the middle of day. Within that circle, daylight fades, temperatures drop a little, and for a brief time, the sun's face is partially or fully covered. These eclipses have long fascinated observers. For much of human history, they were mysterious and unsettling interruptions of the normal pattern of light and shadow. Today, with careful predictions based on orbital mechanics, we understand them as natural alignments. The moon's shadow becomes a precise probe, helping us measure the sun's size and the Earth-Moon distance with high accuracy. At other times, Earth passes between the sun and the moon, casting its own shadow on the lunar surface. During a total lunar eclipse, the moon moves into Earth's umbra, the deepest part of its shadow, yet it does not disappear completely. Instead, it often glows a dim red or copper color, lit by sunlight that has been filtered and bent through Earth's atmosphere. From your spacecraft, you could imagine watching such an event from above. On one side, Earth's limb is lit by the sun, surrounded by a thin ring of atmosphere glowing with sunrise and sunset colors all around its edge. Some of that reddish light leaks into the shadow cone and paints the moon. Light and darkness weave together through gas and geometry to create this gentle spectacle. The way shadows fall during eclipses has helped scientists refine models of the Earth-Moon system. Precise timings of when a shadow begins to cover the sun or the moon allow us to test our understanding of orbits and rotations. Even small changes in Earth's rotation rate, spread over long periods, can be studied by comparing historical eclipse records with modern calculations. From the perspective of your journey, though, these details can simply drift by as interesting shapes. What matters for your rest is the broad idea. Sunlight spreads outward from the sun, Earth spins and orbits, the moon circles Earth, and shadows slip across surfaces and through space whenever one body steps into the path of the light. Letting Earth and Moon recede a little in your mind, you can picture your spacecraft resuming its slow outward drift. The blue and white globe grows smaller in the window, and the moon shrinks to a pale bead beside it. The familiar pattern of 24-hour days and monthly lunar phases stays behind, like a quiet clock you can always return to. Ahead of you waits Mars, the next rocky planet, a world that shares some traits with Earth but carries its own distinct signature of light and shadow. You may imagine the ship adjusting course with the smallest of nudges, enough to slide your path toward that rust-colored sphere. There is no jolt, only the feeling that your attention is shifting gently outward. As Mars grows larger, you notice its reddish hue, the result of iron-rich dust covering much of its surface. Patches of darker rock and brighter polar caps break up the color. The pattern of light and dark across the disk hints at deserts, canyons, and ancient impact basins. As on Earth, one half of the globe is lit, and the other is wrapped in night, with a twilight strip in between. Like Earth, Mars rotates once in a time very close to a terrestrial day, only slightly longer. That means the rhythm of day and night there would feel familiar: sunrise, midday, sunset, and a return to darkness on a similar schedule. The planet also has a tilted axis, not too different from Earth's, so it experiences seasons, with sunlight shifting back and forth between hemispheres over the Martian year. The Martian atmosphere is much thinner than Earth's, made mostly of carbon dioxide with traces of other gases. This thin air scatters less light, so the sky is not as strong a blue. Instead, dust in the atmosphere can give the sky a butterscotch or pinkish tone, and shadows on the ground are somewhat sharper, though still softened a bit by scattered light from the bright sky. Robotic missions such as the Viking landers, the Mars exploration rovers Spirit and Opportunity, the rover Curiosity, and others have shown us what Martian sunlight looks like from the ground. Photographs reveal long, cool-toned shadows cast by rocks and rover wheels, and sunsets where the sky near the sun glows bluish while the rest of the sky stays reddish, the opposite of what you may expect from Earth. That curious sunset color comes from the way fine dust particles scatter sunlight. On Mars, the dust allows more blue light to pass straight through near the sun while scattering red light into the rest of the sky. To an observer on the surface, the sun can be framed by a bluish halo in the early evening, while the surrounding sky glows with warm tones. It is a subtle but striking inversion of familiar patterns. Mars also shows you how storms can reshape light and shadow on a planetary scale. At times, winds lift enough dust into the air to create giant storms that wrap much of the planet. During such events, sunlight is scattered and absorbed by the dust, dimming the surface. shadows fade and blur, and the landscape can sink into a muted, amber dusk even at what should be bright midday. From orbit, spacecraft like Mars Reconnaissance Orbiter have watched these dust storms spread, casting diffuse veils of shadow over valleys and craters. Instruments track how much sunlight is blocked at different heights in the atmosphere, allowing scientists to reconstruct the structure of the storms. Again, by following patterns of illumination and shade, we learn about air, dust, and weather on another world. Below your drifting ship, you can imagine looking down on the Martian poles, where bright caps of frozen carbon dioxide and water ice gleam in the sun. When the polar regions tip into darkness for their long winters, these caps extend and the landscape cools. When spring sunlight returns, the ice retreats, and shadows shift as new patches of bright and dark surface are revealed. Having glanced at Earth, Moon, and Mars, you have now seen how similar basic rules can produce very different experiences of light and shadow. A spinning planet with a tilt, an atmosphere of some thickness, and a particular surface texture will always develop its own style of day, night, and twilight. You can let these examples rest gently at the edge of your thoughts. Your spacecraft continues outward, its motion so smooth that you barely notice it. Behind you, the inner rocky planets follow their paths, each keeping its own schedule of sunrise and sunset. Ahead, the giant worlds wait in the deeper dark, where sunlight arrives weaker and more diffuse. In the next stretch of your journey, you will begin to see how illumination behaves on worlds made mostly of gas and cloud. Your small spacecraft still glides through the quiet dark, and nothing has disturbed your seat or the soft glow of the cabin. You are exactly where you left yourself, wrapped in dim light and gentle silence. Only your point of view has begun to lean outward, toward the deeper reaches of the solar system. Behind you, the rocky inner worlds slowly shrink in the mind's window. Mercury, Venus, Earth, and Mars keep turning under their familiar styles of sunrise and night. Ahead, the space between planets grows wider, and the sun's light thins, spreading out into a softer, more distant glow. You can imagine the ship making a slow, graceful adjustment, curving its path toward the first of the giant planets. There is no feeling of thrust or strain, only a sense that the background stars are sliding almost imperceptibly. Somewhere out there, Jupiter waits, like a softly lit lantern in the dark. As Jupiter grows in your imagination, you may picture it first as you have seen it in pictures, a striped, swirling world of cloud, far larger than any of the rocky planets. Even from a distance, its bands of white, beige, and rusty brown promise constant motion. Sunlight there is weaker than at Earth, but the planet's vast size and bright clouds still make it stand out. Jupiter orbits the Sun at about 5 times Earth's distance, so the sunlight that reaches it is only about a 25th as strong. You can think of the Sun there as a bright, concentrated star rather than a huge, blazing disk. Daylight on Jupiter's cloud tops is still clear and bright, but it has a more subdued quality, as if the whole scene is lit by a lower, farther lamp. Unlike the slowly turning inner worlds, Jupiter spins very quickly. A day on this giant lasts only about 10 hours from one noon to the next. That rapid rotation stretches the atmosphere into long, parallel bands of cloud that wrap around the planet. It also means that sunlight and shadow sweep across its vast surface in a fast, steady rhythm. On Earth, you might watch a sunset unfold over an hour or two. On Jupiter, the same transition from day to night would rush by more quickly at any given point. The planet's wide bulk moves through the sun's beam like a spinning top, so that dawn, noon, and dusk follow one another in a compressed sequence, again and again. The cloud tops that we see are made of ammonia ice and other condensates, stacked in multiple layers at different heights and temperatures. Sunlight filters through those layers, scattering off tiny particles and droplets before bouncing back toward space. Some regions appear bright because they have thick, high clouds, others look darker where deeper layers are exposed. Shadows in this kind of atmosphere are more subtle than the sharp silhouettes on Mercury or the Moon. Instead of crisp outlines on solid ground, you get softer, graded shading within the clouds themselves. One towering cloud can cast shadow onto lower decks, dimming them slightly. Instruments have to tease out these contrasts in order to reconstruct the three-dimensional structure of the storms. The most famous of Jupiter's storms is the Great Red Spot, a vast, long-lived vortex larger than Earth. You can imagine it as an enormous, swirling oval carved into the cloud tops. Sunlight slants across its raised and depressed regions, creating gentle highlights and shadows around its edges, like light glancing across a slowly rotating whirlpool in a painted sea. At the edge of the day side, along Jupiter's terminator, the cloud tops slip from light into night. From your spacecraft, you might look down and see the bands fading into darkness, their patterns dissolving into a featureless black. Yet even on the night side, the story of light and shadow is not finished, because Jupiter's own storms can produce their own illumination. Inside the atmosphere, lightning flashes within deep thunderclouds, sometimes far more energetic than strikes on Earth. These bursts briefly light up patches of cloud from within, casting ghostly interior shadows as peaks and valleys in the storm glow and then fade. Spacecraft cameras have caught such flashes as tiny bright spots on the night side, momentary islands of day in the darkness. Much of what we know about Jupiter's lighting comes from a series of missions. The Pioneer and Voyager flybys gave us our first close-up images of its banded clouds and the way sunlight plays across them. Later, the Galileo orbiter watched storms and shadows for many years, and the Juno mission has been mapping the planet in exquisite detail, using instruments tuned to different wavelengths of light. One particularly beautiful pattern involves the shadows of Jupiter's many moons. As Io, Europa, Ganymede, and Callisto orbit the giant planet, they regularly pass in front of its face from our point of view. When they do, each moon casts a sharp, round shadow onto the cloud tops below, like dark stamps sliding across a softly lit marble. From your spacecraft, hovering in imagination above Jupiter's day side, you might watch a moon's shadow appear at the limb and travel steadily across the bands. That dark spot is night imposed on noon, a small, moving disk where the sun is blocked. When the moon slips away, the patch of cloud beneath returns instantly to daylight, as if someone had removed a fingertip from a lamp. These transits and eclipses are not only beautiful, they also help scientists measure orbits and test gravity theories with great precision. By timing the motion of the shadows across Jupiter's disk, observers can refine the positions and speeds of the moons. In this way, even a simple circle of darkness on a bright background becomes a scientific tool. Out beyond the moons, sunlight reaches dozens of smaller bodies, rings, and bits of debris. Jupiter has a faint ring system, made of dust and small particles. Seen edge-on and from the right angle, these rings scatter sunlight into a delicate glow, almost like a pale halo. When the planet itself casts its shadow on the rings, parts of that halo fade, revealing thin slices of darkness. From the comfort of your seat, you can let these layered images overlap, bright bands and soft cloud shadows, wandering black disks from moon eclipses, faint rings glowing and dimming as they cross into planetary shade. All of it is the same story of beams of light and solid bodies, scaled up to a realm of gas, storm, and speed. When you feel ready, you can imagine your spacecraft sliding farther outward, easing away from Jupiter's bulk. The striped sphere and its tiny bead-like moons recede, taking their restless, quick-turning days with them. Ahead, another giant comes into view, slightly smaller, paler, and ringed with one of the most spectacular systems of light and shadow in the solar system, Saturn. As Saturn grows in your mental window, you notice first its soft, muted colors. The planet itself appears in shades of cream and gentle gold, banded like Jupiter but more subdued. Around it stretches the ring system, thin and wide, catching the sun's light like a carefully tilted sheet of ice and dust. Saturn orbits even farther from the sun, roughly twice as far out as Jupiter. That extra distance makes the sunlight weaker still, only a small fraction of what you feel on Earth. Even so, the rings and upper clouds of Saturn reflect enough light to shine clearly. It is as if someone has turned the dimmer down but polished the surfaces. The planet's atmosphere, composed mainly of hydrogen and helium, supports bands of clouds and storms, though they are generally less strongly colored than Jupiter's. Sunlight pours across the top of this deep gaseous envelope, making gentle contrasts between zones and belts. Storms can rise and fade, casting subtle shadows onto lower layers, recorded by patient orbiters. The rings are where light and shadow become especially dramatic. They are made of countless particles of ice and rock, ranging from dust grains to chunks the size of boulders. Sunlight hitting the rings is reflected and scattered in all directions, making them bright from many viewpoints. Their structure is sliced into many gaps and bands by gravity and resonances with moons. Because the rings are thin and wide, they cast a strong, crisp shadow onto Saturn's upper atmosphere. From certain angles, you can imagine looking down and seeing a dark band stretching across the planet's face, where the rings block the sun. This shadow moves and changes shape as Saturn orbits the sun and as the tilt of the rings toward the light shifts over the course of its long year. At other angles, Saturn itself casts a shadow back onto the rings. The planet's night side creates a dark wedge in the bright ring plane, a missing slice of light. As the seasons advance, that wedge grows, shrinks, and moves, like the shadow of a tree trunk sweeping across a field over the course of a day. Spacecraft images have shown these shapes with exquisite clarity. Much of our understanding of these patterns comes from the Cassini mission, which spent many years orbiting Saturn. Its cameras and instruments watched the rings and planet through changing seasons, capturing how the sun's angle rose and fell. At Saturnian equinox, when the sun lay almost exactly in the ring plane, the rings turned edge on to the sun and cast only a thin, dramatic line of shadow. During that time, even small vertical structures in the rings threw long shadows across the ring material around them. Tiny clumps and waves produced outsized dark streaks, like blades of grass casting long lines at sunset. By measuring those shadows, scientists could estimate the heights of ring features that would otherwise be almost impossible to see. You can picture your spacecraft hovering above the ring plane, looking down on the pale arcs lit by a low sunday. Where the rings curve into the planet's shadow, they dim and vanish into black. Where they emerge again into daylight, they brighten once more, tracing the boundary between illumination and darkness in a broad, graceful sweep. Around Saturn, as around Jupiter, many moons orbit through the light and shadow of the system. Some pass behind the planet into its shadow, experiencing brief nights even while on the side facing the Sun. Others move through the ring plane, crossing bright arcs and faint dust lanes, sometimes casting their own small shadows onto the rings below. One moon in particular, Titan, has a thick, hazy atmosphere rich in organic molecules. Sunlight there is filtered into a deep orange glow, creating soft, muted shadows on its surface of dunes, lakes, and hills. When Titan passes into Saturn's shadow, its upper atmosphere glows faintly in filtered starlight and scattered light from the rings, a dim and otherworldly twilight. Another moon, Enceladus, is small and icy, with geysers that spray water vapor and particles from its south polar region. In backlit views, sunlight passing through these plumes creates glowing veils and cast shadows, revealing fine jets and arches against the darkness of space. By studying the way light passes through and around the plumes, scientists have learned about their composition and structure. From your quiet vantage point, you can let these variations blur into a single, soothing picture, a pale gas giant, wrapped in delicate rings, surrounded by moons that slip in and out of shadow. The Sun is far, but its steady beams still map every curve and surface, drawing long silhouettes and soft gradients wherever something stands in their way. Jupiter and Saturn together show you how distance, speed of rotation, and the presence of rings and many moons complicate the simple idea of day and night. On their cloud tops, day changes quickly, and shadows are often soft and internal. In their ring planes and moon systems, shadows can be sharp, dramatic, and mobile, sliding across surfaces like silent, predictable eclipses. Your spacecraft continues its outward glide, leaving the bright rings and striped clouds behind. The Sun shrinks further and its light grows weaker, but it never disappears. Ahead lie Uranus and Neptune, giants of a different flavor, tipped and chilled, lit by a star that now looks small and intense. Their stories of sunlight and shadow will be even more subdued and subtle. For now, you can rest with the images of the gas giants you have just visited. Broad bands turning under a distant sun, storm tops glowing and fading, moons stamping moving circles of night onto bright clouds, rings painting dark arcs across a soft, golden globe. The patterns are intricate, but you do not need to hold them tightly. They can simply drift with you, as you float deeper into the dark. Your small spacecraft still coasts through the dark, the cabin around you as calm and dim as ever. You have left the bright rings of Saturn behind, and nothing in your seat or in your breathing has changed. Only the picture outside your imagined window has begun to shift, tilting your attention farther from the Sun. Behind you now, Jupiter and Saturn circle like distant lanterns, their clouds and rings still turning under their fast days. Ahead, the Sun grows smaller and sharper, more like a brilliant star than a disk. Its light keeps spreading out, so each step you take into the outer system feels like walking away from a campfire on a cold night. You can imagine the spacecraft making another gentle correction, almost too small to notice, nudging your path toward the next major world. There is no jolt. The stars seem to drift very slowly as your course bends. Somewhere in the deep blue distance, Uranus waits, an ice giant tipped on its side, carrying a very unusual pattern of sunlight and shadow. As Uranus grows in your mind's window, it appears as a pale, smooth sphere with a soft blue-green color. Unlike the banded drama of Jupiter and Saturn, this planet looks more modest, with only faint hints of atmospheric structure. Even so, it shares their basic nature, a deep envelope of gas and icy materials wrapped around a hidden interior, all bathed in faint, distant sunlight. Uranus orbits the Sun at about 19 times Earth's distance, so the sunlight that reaches it is roughly 400 times weaker than the light that warms your home world. You can imagine the Sun out here as a bright, piercing point, smaller than the nail of your thumb held at arm's length, yet still strong enough to illuminate cloud tops and faint rings. The most striking feature of Uranus is its tilt. Unlike Earth, which leans by a little over 20 degrees, Uranus is tipped by close to 98 degrees. Its axis lies almost in the plane of its orbit. You can picture the planet rolling around the Sun like a spinning ball on its side, one pole pointing near the Sun for much of its long year. This extreme tilt reshapes the seasons in a dramatic way. For many years at a time, one polar region of Uranus can face the Sun almost directly, receiving continuous daylight, while the opposite pole lies in extended darkness. Later in the orbit, the situation reverses, and the previously dark pole enjoys its long turn in the light. Day and night, season and shadow blur together. From above the planet, you might see one polar cap brightly lit, the other hidden in a vast, cold night. The boundary between light and dark circles near the equator instead of nearer the poles, depending on the season. The usual pattern you know from Earth, with a spinning globe and moderate tilt, is replaced by something more like a slowly turning wheel under a sideways lamp. The atmosphere of Uranus is made mostly of hydrogen and helium, with a smaller amount of methane. That methane absorbs red light and lets blue and green light slip through, giving the planet its characteristic color. Sunlight passes through the upper haze, scatters from clouds and gas, and returns to space as a soft cyan glow. Shadows within the atmosphere are muted and diffuse, buried inside layers of gas. Because Uranus rotates in about 17 Earth hours, any one point on the cloud tops moves from its local day side to night side fairly quickly, even though the overall pattern of seasonal lighting changes slowly over decades. Daylight there is gentle but clear, and the transition to night is a soft fade rather than a sharp cutoff, softened by scattered light in the air. Faint rings encircle Uranus, much darker than Saturn's shining bands. They are made mostly of small, dark particles that reflect little light. When sunlight strikes them, they show up as thin, dim arcs against the black of space. Where the planet's shadow falls across the rings, sections of those arcs briefly vanish into even deeper darkness, a subtle interplay of weak light and near total shade. Narrow moons orbit close to the rings, shepherding and shaping them with their gravity. These moons, with names drawn from plays and stories, sometimes pass into Uranus's shadow, slipping from faint daylight into sudden night. At other times, they cast small, moving shadows onto the cloud tops below, just as the moons of Jupiter and Saturn do, though the contrasts are gentler here at the fringes of sunlight. Much of what humans know about Uranus comes from a single close encounter by the Voyager 2 spacecraft, along with decades of observations from ground-based telescopes and instruments like the Hubble Space Telescope and the James Webb Space Telescope. These distant eyes watch how light changes on the planet as seasons progress, revealing slow shifts in storms, bands, and polar hazes. From your quiet seat, you can imagine hovering above Uranus's sunlit pole, looking down on an almost featureless disk-tinted blue-green, edged by thin rings. Around the limb, the twilight border curves, separating the bright polar region from the long night that wraps the rest of the globe. It is a calm and restrained pattern, appropriate for a world so far from the sun. When you are ready, you can let your spacecraft drift still farther outward, easing away from Uranus's strange sideways seasons. The pale sphere shrinks behind you, and the already faint sunlight grows weaker. Ahead, Neptune waits near the frontier of the classical planets, another ice giant, deeper blue, stormier, and even more remote in the sun's thinning light. As Neptune comes into view in your mind, it appears as a rich, deeper blue disk, with subtle bands and occasional bright spots. Those bright regions mark storms and cloud systems in its atmosphere. The color again comes from methane-absorbing red light, but details in the clouds and winds give Neptune a somewhat sharper, more textured appearance than Uranus. Neptune orbits the Sun at about 30 times Earth's distance, so the sunlight bathing its clouds is almost 900 times weaker than the light at Earth. Yet the planet still reflects enough of that faint energy to be seen clearly with good telescopes. You can think of its daylight as a pale but steady wash, bright enough to bring out color, too soft to be harsh. Like Uranus, Neptune is made mostly of hydrogen, helium, and icy materials, with methane in the higher atmosphere. Sunlight streaming in from the distant sun passes through these layers, scattering and reflecting from droplets and hazes. Shadows are most evident within clouds. When a tall storm tower rises above surrounding layers, it can cast shade onto the lower decks, producing faint patterns that orbiters and telescopes can trace. Despite its distance, Neptune is active. Winds there can reach very high speeds, and storms can grow and fade over years. One famous example, the Great Dark Spot seen by Voyager 2, was a large storm that later disappeared, while other dark vortices formed elsewhere. These features mark places where the flow of air redirects sunlight and shadow into spirals, bands, and ovals, like weather systems on Earth magnified and placed in a dimmer, colder sky. The boundary between day and night on Neptune, the terminator, curves across the blue disk just as on other planets. From your spacecraft, you could watch the line of twilight slide across the face, dragging the shadow of night behind it. Because Neptune's rotation period is about 16 Earth hours, each point on the cloud top spends a similar amount of time in faint day and faint night. Neptune also has a set of rings and small moons. The rings are dark and thin, broken into arcs in some places, shaped by the gravity of nearby moons. Sunlight striking these dusty bands creates a delicate glow that is easy to lose against the background. Where Neptune's shadow slices across the ring plane, those faint arcs are interrupted, creating thin regions of deeper black that move as the planet orbits. Moons like Triton, Neptune's largest satellite, add their own stories of light and shadow. Triton is a cold, icy world with a thin atmosphere and active geysers that can loft plumes above the surface. When sunlight hits these plumes, they can cast long, feathery shadows across the ground, revealing the height and spread of the jets. Voyager 2 images showed dark streaks on Triton's bright plains, likely created by wind-blown material from such eruptions. On the night side of Neptune and its moons, starlight and the weak reflected glow from the planet create a very gentle illumination. It is easy to imagine these regions as nearly absolute darkness, yet even here, a tiny trickle of light persists. The sun is small but persistent, its beams reaching almost to the edges of the planetary family, still capable of drawing outlines around clouds and rings. Most of what humans know about Neptune also comes from the single Voyager 2 flyby, along with countless hours of telescope time. Each observation records how light is reflected, absorbed, or blocked as the planet rotates and storms evolve. By comparing images taken years apart, scientists see changes in brightness and pattern that reveal the slow breathing of this distant atmosphere. From your resting place in the cabin, you can let Uranus and Neptune blend together in your thoughts as the ice giants, gentle and far away. One lies on its side, rolling through extreme seasons, the other stands more upright, wrapped in fast winds and deeper blue storms. Both are lit by a sun that has faded from overwhelming presence to a small, brilliant ember. As your spacecraft continues outward, there is a sense that you are moving from the fully illuminated rooms of the solar system into its dim hallway. Beyond Neptune lie belts of small, icy bodies, dwarf planets, and comets, all orbiting in the cold outskirts. Sunlight reaches them as a pale glint, enough to make their surfaces shine but not enough to warm them much above absolute night. You might picture the Kuiper belt as a vast, sparse ring of frozen debris and dwarf planets, all slowly circling in the distant dark. Each object there has its own tiny pattern of light and shadow, bright ice reflecting the sun, dark patches absorbing it, craters casting long black shapes across faintly lit ground. The geometry is the same, but the scale of the light has shrunk. Some of these distant worlds occasionally swing inward on elongated paths, becoming comets. As they approach the sun, ice on their surfaces begins to vaporize, and sunlight pushes on the dust and gas that stream away, forming tails. Those tails always point roughly away from the sun, shaped by light and the solar wind, while shadows fall across the solid nucleus itself. Even here, light sculpts form and motion. Spacecraft such as New Horizons have flown through these outskirts, giving humans their first close looks at faraway bodies like Pluto and Arrokoth. In the images they returned, you can see delicate contrasts of light and dark on frozen landscapes, long shadows from cliffs, and smooth plains that shine more brightly than rougher terrain. Every pixel is a record of how weak sunlight interacts with strange, cold surfaces. From your ship, resting in imagination beyond Neptune, you could look back toward the sun and see all the planets you have visited compressed into a tiny region around a bright point. Their varied patterns of sunlight and shadow, from Mercury's sharp silhouettes to Neptune's dim clouds, all fit within that small, shining system. The outer darkness stretches even farther beyond. You do not have to hold all of these worlds firmly in mind. They can drift past like slow scenes outside a train window at night, each lit in its own way by the same distant star. What matters is the gentle realization that even far from home, sunlight still reaches out, and shadows still mean something, tracing shapes on every world. Your spacecraft remains a quiet cocoon, humming softly, its interior dim and steady. You are wrapped in the same stillness you had near Earth, only now your thoughts have walked the length of the planetary family. In the remaining parts of this journey, you will turn from specific worlds toward the larger story they tell together, letting their patterns of light and shadow hint at how solar systems form, evolve, and perhaps support life. For now, you can let the image of the distant sun rest behind your closed or half-closed eyes, a small bright point pouring out rays that never quite stop. Somewhere in those rays, all the planets continue their slow turning under day and night, while you float in the dark, free to drift with them or to sink more deeply into sleep. Your small spacecraft still rests in the enormous dark, and nothing inside the cabin has changed. The panels give off the same soft glow, the quiet hum stays steady, and your seat holds you in the same gentle way. Only your thoughts have traveled, walking slowly from one world to the next and then outward into the cold edge of the solar system. If you imagine looking back through the window, the sun is now a bright point surrounded by a cluster of tiny, invisible paths. Each planet is somewhere along one of those paths, turning, tilting, and trading day for night. Mercury, Venus, Earth, Mars, the giants, and the distant ice all continue their quiet pattern of sunlight and shadow whether you are watching or not. You have seen that the same basic rules play out in very different ways. A planet's distance from the sun, its spin, its tilt, its moons, its atmosphere, and its rings all change how light falls and how darkness gathers. The result is a family of worlds where noon can mean blinding glare, hazy brightness, dusky gold, or soft blue twilight. Now, as you float beyond Neptune in your imagination, you can let your attention turn from one planet at a time to the larger story they share. The patterns of illumination that help you drift from world to world also carry clues about how these worlds formed, how they evolved, and which of them could ever host living things. Imagine the solar system not as it is now, but as it once was, a young star forming in a cloud of gas and dust, surrounded by a flat, spinning disk. In that disk, particles orbited the growing sun like fine smoke in a slow whirl. Sunlight was already streaming out, heating the inner regions more strongly than the outer parts. Close to the sun, temperatures in the disk were high enough that many kinds of ice could not survive. Rock and metal grains stayed solid, but water and other volatiles tended to vaporize and linger as gas. Farther out, where sunlight was weaker and the disk was cooler, those ices could remain frozen, adding to the solid material that could clump together. This simple gradient in warmth, set by distance from the new sun, helped divide the solar system into zones. Near the star, small rocky planets assembled from the harder materials. Farther away, beyond a region sometimes called the frost line, large cores could gather lots of ice as well as rock and then draw in thick envelopes of gas, becoming giant planets. You can picture this process as a slow sorting by sunlight. Where light was intense, surface layers of the disk lost lighter elements and ices, leaving behind sturdier grains. Where light was weaker, frozen materials could accumulate, and more mass could gather. Over millions of years, these differences grew into the variety of planets you have just visited in your mind. Even now, the way each planet reflects and absorbs sunlight carries traces of that history. Mercury and the Moon, dark and airless, show you surfaces that have been exposed to space for billions of years, baked and bombarded. The gas and ice giants, with their thick envelopes and deep, unseen interiors, still wear the imprint of icy planet formation far from the sun's heat. As your spacecraft drifts, you can imagine the sun's light as something like a universal tracer ink. By watching how that light bounces off a world, how much is reflected, and in which colors, scientists can infer what that world is made of. This reflective quality is sometimes called albedo, and each planet has its own characteristic brightness and tint. High albedo surfaces, like Venus's clouds or Saturn's rings, shine strongly under sunlight, returning a large fraction of what they receive. Darker surfaces, like the basaltic plains on Mercury or the sootier regions of comets, absorb much more and reflect less. The balance between absorption and reflection helps set surface temperatures and drives the flow of heat. You have already seen how atmospheres complicate this simple picture. An atmosphere can scatter sunlight in all directions, brighten a sky, form clouds that reflect light, and trap infrared radiation trying to escape. On Earth, this greenhouse effect keeps the surface much warmer than it would be if the planet were a bare rock, reshaping how day and night feel. Venus shows an extreme version of this greenhouse trapping, with thick carbon dioxide and clouds of sulfuric acid locking in heat. Mars, with a thin atmosphere, shows a more fragile case, where heat can escape more easily. As you think about these three neighbors together, you can feel how the same sun, shining with the same strength at their distances, produces very different climates through the filter of air. From your quiet seat, you do not need equations to follow this. It is enough to picture sunlight as a stream of energy that arrives in visible light and leaves in longer wavelengths. If a planet's surface and atmosphere let most of that energy escape, the world stays cold. If the atmosphere holds some of it back, the world warms, changing where ice, liquid, and gas can exist. This balance is central to what scientists call the habitable zone, the range of distances around a star where an Earth-like planet might support liquid water on its surface. It is not a fixed, sharp-edged ring, but a concept that depends on how much light the star emits and how the planet's atmosphere behaves. Our Earth happens to sit in such a zone around the Sun. You can imagine that zone as a gentle band around the Sun, stretching from inside Earth's orbit to a region beyond. At the inner edge, a world risks becoming too hot, its oceans evaporating and its atmosphere thickening. At the outer edge, a world risks freezing, with water locked into ice. Between those extremes lies a region where day and night can support familiar seas and rains. In your journey so far, Earth is the only planet that clearly lives in this comfortable band with the right kind of air. Mars sits near the outer edge. In the past, it may have enjoyed periods when thicker air and stronger greenhouse warming allowed liquid water to flow, leaving valley networks and river deltas. The faint sun, distance, and time have gradually pushed it toward a colder, thinner-aired state. Seen in this way, the patterns of sunlight and shadow you imagined on each world become more than pretty pictures. They are clues to deeper questions. Where can water remain liquid under the daily cycle of heating and cooling? Where can complex molecules persist? And where might living systems adapt to the gentle, regular pulse of day and night? As your spacecraft floats at the edge of the system, you can let your mind reach even farther, out to planets that orbit other stars. For these exoplanets, scientists cannot visit in person, but they can still learn about light and shadow by observing the tiniest changes in starlight when a planet passes in front of its star. During such a transit, a planet casts a small shadow on its star, from our point of view, and the star's brightness dips slightly. By measuring how deep and how long that dip is, we humans can infer the planet's size and orbit. It is a distant echo of watching a moon's shadow slide across Jupiter, or Mercury crossing the Sun, but now on a scale of entire other systems. Sometimes, instruments can even detect the faint change in starlight as it filters through a planet's atmosphere during a transit. Different gases absorb light in different colors, leaving fingerprints in the spectrum. By studying those fingerprints, scientists can begin to guess what kinds of air wrap some exoplanets, and whether those airs could support familiar patterns of clouds, rain, and perhaps life. In a few special cases, telescopes have directly imaged exoplanets as tiny points of light near their stars. There, too, sunlight and shadow define what we see. We are looking at reflected starlight bouncing off a distant world or at heat the planet radiates after absorbing that light. Even the faintest dot is a testimony to the same geometry you have followed from Mercury to Neptune. From your calm vantage point, you might picture a galaxy as a vast, dark field filled with stars, each one sending out its own beams of light. Around many of those stars, planets orbit, tilting, spinning, and casting shadows just as in our own system. The specific details differ, but the underlying interplay of illumination and darkness repeats on a grand scale. This repetition is reassuring. The way sunlight falls on the worlds you have imagined is not random. It reflects simple physical laws that apply everywhere. Straight-line travel of light, gravity's shaping of orbits, conservation of energy, and the properties of matter all work together to create the shifting carpets of day and night. You are watching a consistent pattern play out in countless variations. Scientists use this consistency to test their understanding. If the same equations that describe Earth's orbit and seasons also predict the length of a Martian day, the tilt of Saturn's shadows, or the timing of an exoplanet's transit, then those equations are likely capturing something real about the universe. Light and shadow become a kind of quiet, universal language that nature uses to reveal its structure. You can imagine mission planners and astronomers working late under soft office lights, poring over images of dim arcs, dark spots, and glowing rims. To them, each careful measurement of a shadow's position, each curve in a brightness graph, is a step toward answering larger questions: how solar systems form, how long they remain stable, and where the conditions for life might appear. From your perspective in the cabin, the details can remain fuzzy at the edges, like dreams you do not need to pin down. What matters is the broad picture. The same star that sets your own circadian rhythm also sculpts the climates of neighboring planets. The same logic that explains an eclipse in your sky helps decode the existence of distant worlds. If you let your awareness drift back to your own body for a moment, you can notice how deeply you are tied to light and dark. Your internal clocks respond to sunrise and sunset, to bright days and dim evenings. Many forms of life on Earth tune their behavior to the length of the day, the angle of the sun, and the presence of twilight. Biological rhythms echo the rhythm of illumination. Viewed from space, Earth's day and night patterns are just one more instance of light sweeping across a rotating sphere. Yet from the inside, those patterns cradle forests, oceans, cities, and individual lives. The frontier between sunlight and shadow carries songs of birds, the closing of flowers, the flick of street lamps, and the quiet settling of people into sleep. This is one way that the abstract patterns you have followed become personal. You, lying or sitting here, are shaped by the sun just as strongly as any crater or cloud band. You are simply more intricate, with thoughts and feelings that respond to light in ways that go beyond mere temperature. Your own waking and resting are a small echo of the planetary ballet. As you rest in your imaginary spacecraft, it is gentle to realize that you do not need to control any of this. The sun will continue to shine, planets will continue to turn, and shadows will continue to slide along their surfaces whether or not you pay attention. The universe carries the pattern for you, leaving you free to let go of the details. In the next stretch of this quiet journey, your thoughts will turn even more toward time, how these patterns of illumination change over billions of years, how stars brighten and dim, and how planetary climates and orbits slowly drift. For now, though, it is enough to feel that everything you have seen, from bright Mercury to dim Neptune, fits together in a single, calm design of light and shade. You can allow that design to blur at the edges, leaving only a soft impression, a small star in a huge dark, surrounded by worlds, each carrying its own slow breathing of day and night. Your spacecraft remains a peaceful cocoon in that dark, and you are welcome to stay with the faint image of that star, or to let the image fade entirely as you sink more deeply into rest. Your small spacecraft still drifts in the same quiet dark, and the cabin around you remains unchanged. The panels glow softly, the faint hum is steady, and your body is held in the same easy rest. Only your attention has been moving, following sunlight and shadow from the inner planets to the icy outskirts and into the wider patterns that bind them. Now, floating in imagination beyond Neptune, you can let your thoughts turn from space to time. Light on each world is not only different from place to place, it is different from age to age. The sun itself changes slowly, and the orbits and spins of the planets shift, so the rhythms of day and night, season and climate all drift over immense spans of years. You can picture the solar system long ago, when the sun was younger and a little dimmer. The same star that now lights your days once shone more weakly, so that every planet received less warmth. The disk of gas and dust that formed the planets had mostly cleared away, but impacts were still more common, and craters were being carved into surfaces that would later lie in quiet shadow. On Earth, in that young era, days were shorter. The planet spun faster, so the sun would have crossed the sky more quickly, and shadows would have swept over the landscape at a brisker pace. Tides from the moon and the sun acted like a slow brake on the rotation, gradually lengthening the day as energy from the spin was transferred to the orbital dance of Earth and Moon. You can imagine the moon closer then, appearing larger in the sky, its own day and night cycles locked to its orbit around Earth. Over hundreds of millions of years, that orbit expanded as the tides tugged gently at the oceans and crust. The moon's shadow during eclipses still crossed Earth, but the geometry of light and dark shifted slightly with each small outward step. As Earth's spin slowed, the shape of daily light changed for every living thing. The alternation between day and night grew longer and perhaps more moderate, giving biological cycles new patterns to adapt to. Plants, animals, and microscopic life tuned their internal clocks to these evolving rhythms, learning to expect sunrise and sunset on a schedule that itself was drifting through deep time. Seasons on Earth have also changed in subtle ways over long spans. The tilt of Earth's axis wobbles slightly, the shape of its orbit varies between more circular and more stretched, and the orientation of that orbit shifts. These slow cycles, sometimes called orbital variations, alter how sunlight is distributed between latitudes and seasons, nudging the planet into and out of ice ages. From your quiet seat in the cabin, you can imagine ice sheets advancing and retreating under changing light, shadows from mountains falling across growing glaciers and then across exposed rock again when the ice melts back. The sun itself does not flicker quickly, but tiny shifts in how its light meets Earth can build up over tens of thousands of years into large climatic swings. Other planets have their own long dances of illumination. Mars, with its modest tilt and thin air, experiences significant changes in climate as its orbit and tilt vary. When conditions favor it, ice can extend away from the poles and dust can be rearranged across the surface, altering how much sunlight is absorbed or reflected. The length and character of Martian shadow can change with each such cycle. Venus offers a different, more mysterious story. Its thick atmosphere hides the surface from direct view, and its slow, backward rotation produces very long days and nights. Some scientists suspect that, early on, Venus may have had milder conditions and perhaps even liquid water. Over time, As the sun brightened and greenhouse gases built up, its climate shifted into the intense regime you imagined earlier, with a permanent, blazing daytime at the surface. In the outer system, seasonal changes are stretched out over long years. Saturn's rings, for example, tilt slowly toward and away from the Sun as the planet moves in its wide orbit. Over decades, the pattern of ring shadows on the planet and planetary shadows on the rings evolves, so that a photograph taken in one century can look quite different from one taken in another. As you drift farther forward in time with your thoughts, you can imagine the Sun continuing its slow evolution. Over billions of years, a star like the Sun gradually becomes brighter as it uses up hydrogen in its core. That means the same distance from the Sun receives more light in the far future than it does now. The habitable zone around the star migrates outward as the star ages. For Earth, this brightening has consequences, but on timescales so long that they remain abstract and distant. At some future point far beyond any human planning, the increase in sunlight will likely make it harder for oceans to remain liquid at the surface. Water may gradually be lost to space, and the pattern of familiar blue seas and white clouds will fade into a different kind of world under a harsher sun. From your calm vantage point in the spacecraft, these changes are like chapters in a book shelved many rows away. They are real and part of the story, but they are not immediate. The Sun's present brightness supports the climates and ecosystems you know, and any shift toward those hotter conditions lies on a timeline that dwarfs human history by orders of magnitude. Much farther in the future, the Sun will eventually exhaust the hydrogen in its core and swell into a red giant. Its outer layers will expand, and its light will become both more intense at nearby distances and redder in color. The inner planets will be engulfed or stripped of their surfaces. Shadows, as you understand them now, will be replaced by a different, more chaotic illumination near the star. The outer worlds may, for a time, receive more warmth under that enlarged Sunday regions that are now deeply frozen could experience milder conditions, at least briefly. Frozen ices on distant moons and dwarf planets might melt or vaporize under the increased light, reshaping surfaces and creating temporary atmospheres, with new patterns of day and night weather. Eventually, the Sun will shed its outer layers and shrink into a dense, hot remnant called a white dwarf. Its light will again become fainter at the planet's distances, though its temperature will be high at the surface. The surviving worlds will orbit a much smaller, dimmer star, and the illumination across their landscapes will be reduced to a pale echo of the bright days you know. If any planets remain in stable orbits then, their days and nights will still alternate as they spin, but the difference between day and night might feel more like the difference between dusk and deep dusk. Shadows will be lighter, and the warmth of the star will barely lift surfaces from the cold background of space. Yet even here, light and darkness will still trace the turning of spheres. Over these immense spans, the spins and orbits of planets continue to evolve. Tidal forces between each planet and its star, and between planets and their moons, can slowly change rotation rates. Days can lengthen, and in some cases, worlds can become tidally locked, always showing the same face to their star, like the Moon does to Earth now. On a tidally locked planet, one hemisphere would live in perpetual day, fixed under the star, while the opposite hemisphere would lie in permanent night. The frontier between them would be a ring of eternal twilight, where the star sits forever on the horizon. The pattern of light and shadow would be frozen in place, yet air and heat might still flow, carrying a dynamic climate around the globe. In your own solar system, you have already seen hints of such states. Mercury is caught in a spin-orbit resonance, turning a specific number of times for each orbit. Many moons around the giant planets are tidally locked, always presenting one side to their parent worlds. These configurations are the end result of long, slow exchanges of energy, traced by the changing shapes of shadows over eons. Gravitational interactions among planets also matter over deep time. Orbits can shift slightly as planets tug on one another, changing distances from the Sun and altering the pattern of sunlight they receive. In some scenarios, minor bodies are nudged into new paths, becoming comets or being ejected entirely, carrying their private patterns of day and night out into interstellar space. From your quiet seat, you can view all these possibilities as gentle variations on a theme rather than as disasters. The universe is not fixed, but its changes, especially on stellar scales, are gradual, more like the slow turning of a page than the sudden flipping of a switch. Light gently rearranges itself across surfaces and atmospheres while the underlying rules remain steady. Scientists study these long futures and deep pasts by combining observations with models. They track how stars like the Sun evolve, how planetary orbits respond to gravitational pulls, and how atmospheres react to changing light. Computer simulations turn equations into moving pictures of climates, day lengths, and seasonal cycles drifting over millions and billions of years. These models are not perfect, and many questions remain open. Exactly how Earth's climate will respond to future changes in sunlight, precisely how Venus became so different from its neighbors, or whether Mars could be coaxed into a more hospitable state are all active areas of research. Light and shadow carry clues, but they do not give up all their secrets easily. Other unanswered questions reach beyond your own star. How common are stable, long-lasting habitable zones around different kinds of stars? How many planets hold their tilt and spin within a range that gives them gentle seasons rather than wild swings? How often do atmospheres persist long enough for life to arise and adapt to day and night? Each exoplanet transit and spectrum adds a small hint. From the perspective of your imaginary spacecraft, these questions are like distant constellations of thought. You do not need to chase them. You can simply notice that every world's pattern of light and shadow is both a snapshot in time and a frame in a longer movie. The scenes you have visited are just a few stills from that slow, unfolding film. If you turn your attention back inward for a moment, you might notice how your own sense of time feels right now. Perhaps minutes blur together, and the idea of billions of years feels more like a soft fog than a sharp number. That is all right. Your mind is allowed to treat cosmic time as a backdrop rather than a puzzle to solve. The key feeling is simple and quiet. Stars are born, burn, and change. Planets spin, tilt, and wander. Light grows stronger and then weaker. Shadows shift their shapes, and through it all, the underlying patterns remain. Straight beams from a star, turning spheres, and the geometry of orbits create endlessly varied but familiar rhythms of day and night. In the final stretch of this journey, you will turn more directly toward your own place in this pattern. You will think not only about planets and stars, but about how it feels to live under one particular sun, on one particular world, with its specific cadence of sunrise and darkness. The story will narrow from the cosmos back down to the level of your own resting body. For now, you can let the immense timeline soften and drift to the edges of your awareness. Imagine the sun as a small, bright point far behind your closed or half-closed eyes, and the planets as tiny beads slowly circling it. Their days and nights continue at their own paces, while you remain here, still and safe in your quiet cabin, free to let sleep come whenever it chooses. Your small spacecraft still floats in the same deep dark, and the cabin around you is as quiet as ever. The panels give off their soft, steady glow, and the hum beneath your seat has not changed. Only your thoughts have been moving, wandering slowly through the solar system and then farther out into the long story of time. You have traced sunlight and shadow from the scorched days of Mercury to the hazy glow of Venus, from the blue and white swirl of Earth and its moon to the dusty skies of Mars. You have skimmed past the vast clouds of Jupiter and Saturn, the pale ice giants, and the dim outskirts where faint worlds turn under a distant sun. All along, you have been following one gentle question: how does sunlight touch each world, and what do those shifting patterns of light and dark reveal about the planets we call our neighbors? The answer has not been a single phrase, but a feeling that grew clearer each time you pictured another sunrise or another shadow. You have seen that distance from the sun sets the strength of the light, like moving closer to or farther from a campfire on a cold night. You have seen that the spin of a planet and the tilt of its axis decide how days and seasons unfold. You have seen that air and cloud can soften or sharpen every line of shade. On some worlds, daylight is fierce and shadows are knife-edged, as if carved into rock by the sun itself. On others, thick air scatters light so deeply that day feels like standing inside a glowing mist, and shadows become soft suggestions instead of clear shapes. The same star creates very different moods wherever it shines. You have watched in your mind as rings cast long, graceful bands of darkness across cloud tops, and as moons stamped round, moving spots of night onto bright planets. You have drifted over polar caps where the sun barely rises and over equatorial regions where day and night trade places with steady regularity. You have listened to the idea that these patterns are not just pretty scenes. They are clues to history and structure, where ice can survive, where oceans might once have pooled, where atmospheres can hold heat, and where life could learn to live under a gentle rhythm of dawn and dusk. Light and shadow keep quiet records. From far outside the system, you pictured the sun as a small, bright point, with all the planets packed close around it from this great distance. Every place you visited turned out to be another example of the same simple rules: straight beams of light, turning spheres, orbits shaped by gravity, and materials that absorb or reflect. You then let your thoughts stretch across time, imagining days that were shorter and suns that were dimmer, moons that were closer, and ice sheets that advanced and retreated under shifting skies. You imagined long futures with brighter suns, altered seasons, and new balances between warmth and cold on now familiar worlds. In that long view, the patterns you traced became frames in a slow film. Each moment of day or night on any planet was a tiny piece of a story that runs for billions of years. Planets spun down, tilts wobbled, orbits shifted, stars grew and changed, and through it all, light continued to mark the passing of time. Now, in this final stretch of your journey, you let the film pause and narrow. Instead of trying to hold the whole solar system in your awareness, you gently turn your attention back toward one particular world and one particular place, the small planet where you live and the single body that is resting here and now. In your mind, the spacecraft has turned so that its window looks back toward the inner system. Somewhere along a thin orbital path lies Earth, glowing blue and white on its day side and scattered with city lights on its night side. A soft, moving band of twilight wraps around it, the quiet border between sunlight and shadow. You can imagine drifting closer again, just enough that the curve of the planet fills more of the window. Clouds move slowly across oceans and land. On one side, mid-morning or afternoon light washes the surface. On the other, midnight darkness hides details and reveals strings of artificial stars along coasts and roads. At the edge of the bright half, the sun is low for countless people and places. Shadows stretch along streets and fields. Windows glow as lights come on. Birds settle into trees. Somewhere, someone steps outside to feel the last warmth of the day. Somewhere else, the first pale hints of dawn are just beginning to grow. For every person on the planet, the same pattern repeats in its own way. Sometimes you are awake for sunrise, sometimes for sunset, sometimes you miss them both behind clouds or busy hours. Yet your body still feels the rhythm. Your eyes and brain quietly track how bright the world is, and your internal clocks take note. Right now, as you listen, your body is doing the same thing. It is noticing that the light around you is low, that your attention has turned inward, that sounds are softer than at midday. Signals move through the systems that manage alertness and sleep, letting muscles loosen and thoughts slow, whether or not you describe it. If your eyes are open, the dimness and the steady, unflickering light tell your brain that it is time to wind down. If your eyes are closed, your inner world still reflects the outer rhythm. Images come and go more slowly. Memories blur into each other. The line between focused thought and drifting daydreams grows thin. You do not have to force any of this. The same laws that keep planets turning and shadows moving also keep your internal rhythms running, as long as you give them a little space. Just as you do not push Earth along its orbit, you do not need to pull yourself towards sleep. You can allow gravity, time, and chemistry to help. As you rest in the spacecraft cabin, you might notice the feel of your weight in the seat or the bed beneath you, the way fabric touches your skin, the temperature of the air around your face. You might notice the slow rise and fall of your breath, the tiny pause at the top of each inhale, the gentle release of each exhale. If you wished, you could return once more to the planets. You could think again about Mercury's long sunrises, Venus's glowing clouds, or Saturn's ring shadows. But you have already traveled there. You have followed the thread of sunlight and shadow across those worlds, and you have followed it far enough for tonight. You do not need to remember every fact or every scene. You do not need to keep track of which moon cast which shadow or how long a day lasts on each planet. Those details can fade like the memory of a dream in the morning. What remains is a simple understanding that every world lives under its own style of light and dark. In the same way, you do not have to hold on to each sentence you are hearing now. They can pass through like a gentle breeze or like faint stars in your peripheral vision. Some phrases might linger for a moment. Others may vanish as soon as they arrive. There is no test and no expectation, there is only this quiet time. If your thoughts wander away from the story toward something else entirely, that is welcome. A stray memory, an image, or a fragment of music may rise up. You can let it come and go without effort. The story of planets and sunlight will keep itself. You do not have to choose between listening and drifting, both are allowed. If you notice worries or planning thoughts stepping forward, you can gently set them alongside the planets you have been imagining. They can orbit out there for a while, circling in the dark at a safe distance. You do not have to solve anything before you rest. Problems and plans can wait in that wider space. Meanwhile, your breathing can stay slow and comfortable. Each exhale can feel like a small release, as if you were letting used sunlight leave your body, making room for fresh, cool air. Each inhale can feel like a calm gathering in, no urgency, no rush, just enough for this moment and the next. You are still in that small, safe spacecraft, even if the image is now faint. Outside, the universe is vast and mostly dark, filled with stars that send out light in every direction. Inside, you have only a modest glow, a comfortable place to rest, and the knowledge that you are allowed to do nothing at all right now. You have followed a path that began near the sun and arched outward through every major region of the solar system, then looped back toward your own world and your own experience of day and night. That loop is now gently closing. There is nowhere else you need to travel in your thoughts tonight unless you wish to. If sleep has already begun to blur the edges of the story, that is perfectly all right. If you find that you are still more awake than you would like, that is all right too. Either way, you can stay here, in this quiet place, without needing to move, fix, change, or improve anything about this moment. Outside the imaginary window, you can picture the planets continuing their turns under the sun. Mercury still rotates slowly in its tight orbit. Venus still glows under its clouds. Earth still spins under a moving band of twilight. The giants still wear their storms and rings. None of them asks for your attention. The sun also continues its steady shining, not hurried by your waking or your resting. Its rays travel outward in straight lines, whether anyone watches them or not, writing patterns of light and shadow on worlds near and far. Your resting does not interrupt any of this. The universe is quite capable of running on its own. Knowing that nothing depends on your effort for a while can be a relief. You can let your mind be as quiet or as noisy as it wants, without needing to steer it. If thoughts slow, that is fine. If they spin for a bit and then fade, that is also fine. You are simply here, in the dark, with a long, gentle story behind you. When you feel ready, you can let even the image of the spacecraft drift away if you like. The hum can fade, the panels can dim, the window can become empty. All that remains is the sense of being safe and supported, breathing in and out. There is no need for a vessel when you are not going anywhere in particular. You might find it soothing to imagine a last view of the solar system from far away, a tiny star in a huge night, encircled by worlds too small to see at this distance. Somewhere on one of those worlds, you are lying or sitting, listening, or already asleep, sharing in the same simple rhythm of light and dark as everything else. You have followed this story as far as you need to tonight. You do not have to carry it with you into sleep. You can let it rest, like a book closed quietly on a bedside table, knowing that the pages will still be there whenever you care to open them again, whether that is tomorrow or some other night. For now, there is only the darkness around you, the softness beneath you, and the steady pattern of your breathing. The universe is continuing its slow, graceful motions, but you do not have to follow them anymore. You are free to let your attention loosen, to let your body sink, and to let your thoughts grow very quiet. If sleep arrives, it can feel like slipping into the shadowed side of a planet, turning gently out of the sun's glare into a calm, cool night. If it takes its time, you can simply keep floating here, unhurried, watching darkness and comfort gather around you without any expectation. Whether you are moments away from sleep or still drifting toward it, this journey is complete for now. The sun will rise and set, planets will spin, and shadows will move across distant worlds, all without needing your help. You can rest in that knowledge, and allow yourself to fade softly into whatever comes next.